Jai Hind and welcome to all. Myself Shiwani from Ajay Kumar Garg Engineering College will deliver a lecture on IR spectroscopy in this session, and which is a part of Unit 2 spectroscopic techniques and its application. And for this topic I preferred the following books or references: Elementary Organic Spectroscopy by Y.R. Sharma, Engineering Chemistry by Shashi Chawla, and Principles and Practices of Analytical Chemistry, F.W. Fifield, 5th edition, and Wikipedia. This. So, IR is infrared spectroscopy. I have already discussed this diagram in previous lecture, and where the energy level which have very small gap, which are rotational energy level, these are associated with vibrational energy level, and the group of vibrational energy is associated with ground state as well as excited state. So, atoms or atomic groups in a molecule are in continuous motion, and these energy levels are quantized, that is a fixed amount of energy is required for excitation in a particular energy level. With respect to one another, IR spectra originate from the different modes of vibrations and rotation of a molecule, whereas UV visible absorption bands are primarily due to electronic transition. So, in IR spectroscopy we get a basically strong IR band, while in UV visible a strong band, and there are few another bands which are due to vibration and rotation. While in UV visible spectroscopy we get a band, UV absorption band, and which is basically due to electronic transition, and this is spectroscopy studied whenever transition occurs in vibrational energy level. So, first, what is IR spectroscopy? This spectroscopy is very useful to predict the structure of a known compound or to find out the functional group, because a particular functional group it is absorb the IR radiation at fixed frequency. For example, if suppose IR frequency is about 1700, so we can say that it is due to presence of carbonyl group, and if it is between 3200 to 3400 or 3600, then we can say that OH group is present, because OH group absorb the IR frequency at this range. So, IR spectra is often characterized as a molecular fingerprint, and because we can establish the identity of compound with the help of this spectra. For IR spectroscopy we can say that IR spectra of two compound can never be same except in enantiomer, because in an enantiomer the structure arrangement is same, it is identical, but the behavior towards plane polarized light is different. No two molecule have overlapping IR spectra. Different functional groups present in a molecule, recognizable peaks at nearby definite positions in IR spectra, and most of the IR peaks in IR spectra can be assigned due to presence of a specific group in a molecule. As I have already discussed that suppose peak observed at 1700, near 1700, then definitely it will be due to presence of carbonyl group. Now, so what is the range of IR? So, IR portion of electromagnetic spectrum is usually divided into three regions: IR region, and then far IR and near IR. The main IR region, it extends from 667 approximately inverse to centimeter inverse to 4000 centimeter inverse. And if we go towards higher level, that is above 4000 up to 12,500 centimeter inverse, it is known as near IR, and below the lower value, that is 667 lower up to 50 centimeter inverse, it is called far IR region. And near IR region, it can excite overtone or harmonic vibrations, and what is the overtone I will discuss after the when I discuss the types of stretching and banding. So, the range is 667 to 4000, above 4000 up to 12,500 is near IR, and 667 to 50 it is far IR. The absorption of IR radiations which are quantized. Quantized means a fixed amount of energy is required for a excitation. If the molecule get that fixed amount of energy, the transition will occur, otherwise not. It causes the vibration bands in a molecule due to stretch and band with respect to one another. It means in IR spectroscopy, we consider the atom as a balls, and the bond between the atoms are like a spring. So, just like a spring can be stretched or bent, the same thing, the bonds between the atoms, they can be stretched or bent, and due to this stretching or bending we get a IR spectra. And next, another thing in IR spectra or IR spectrum, it is observed, it is generally find or draw with respect to transmittance versus wave number. Instead of absorption, in IR spectrum we prefer the transmittance, we prefer the transmittance, and on this side we prefer wave number. Although the wavelength and wave number both are reciprocal, if we know the wavelength we can find the wave number, because the lambda is equal to 1 upon nu bar, and the absorbance it is equal to log of 1 upon T. So, all these things are basically interrelated. If we know the absorbance, we can find transmittance, and if we know the wavelength, we can find the wave number. But since the energy is directly proportional to wave number, so we can find we can correlate the energy with the help of this wave number. This technique is very useful for identification of structure of new compound having certain functional groups. The stretching frequencies are higher than. If we take a spring and we stretch this, so it is easily we can see that for stretching higher amount of energy, high energy is required, and that is why stretching frequencies they are observed at higher frequency as compared to bending frequency. Bonds to hydrogen have higher stretching frequency than those of heavier atoms. I will discuss this point. IR radiation is largely thermal energy, and it induces the strong molecular vibration in covalent bonds. In a molecule, if we irradiate with about 100 centimeter or 100 centimeter inverse wave number or frequency, then we see that there is a excitation only in molecular energy level, and for this we get a rotational spectra, and after this or above 100 centimeter inverse we can get the spectra due to vibration or rotation. But at the higher value of energy or higher value of frequency, we see that the spectrum occurs only due to vibrations, and we can basically we can say that this type of bands or spectrum is IR spectrum. The specific bond respond to specific frequency. Stretching is like this. This is the equilibrium bond length, and if we stretch the bond, it is like this. If we compress, then like this. So, we will discuss all this stretching or banding in next slides. But before this, it is a point then which type of molecule will give IR spectra. So, the concept is only those type of molecules which have permanent dipole moment or dipole moment get changed during vibrations, because in IR we see that there is a transition in between vibrational energy level. So, those molecule where whose dipole moment change during vibration, they absorb the IR radiation or they show the IR spectra. Symmetrical molecules like O2, F2, H2, Cl2, their dipole moment is 0. So, that is why they do not absorb IR radiation. So, they are called IR inactive. It means IR active are those compound which have permanent dipole moment or dipole moment change during vibration. So, they are IR inactive, that is they will not show IR spectra. Diatomic molecules which show dipole moment like HCl, Cl is more electronegative than hydrogen, then definitely there is a polarity. So, they show dipole moment, HCl, HF, CO, HI, all these molecules they are IR active. So, the condition is molecules with more than one atoms may or may not be IR active depending on whether they have permanent dipole moment. There are few questions. Which of the following molecules will be IR active? N2, dipole moment 0, permanent dipole moment no. So, it is inactive. In case of CO2, if we see the structure, it has linear structure. So, if bond stretching is like that, that dipole moment becomes 0, that is no net dipole moment change, so this type of stretching will be inactive. And if the stretching is like this, that net change in dipole moment, so this will be IR active. But simply we can say it is IR active. OCS again IR active, H2O bent structure. So, if we stress the bond or bend the bond, definitely dipole moment change. So, it is again active. CH2 double bond CH2, it is symmetrical structure. So, it is inactive. Benzene, we can say it is active because of double bond this. So, double bond and triple bond CH2, this they do not absorb IR energy. Why? Because they have symmetrical structure and there is no net dipole moment or dipole moment change during vibration. Methanol is a good solvent for UV, but not for IR determination. Why? In IR determination, methanol shows IR spectra because of polarity, because of dipole moment change. That is why it will show IR spectra. So, it is not good for IR determination. Methane does not absorb IR energy. In methane, all the bonds are similar. So, no dipole moment, net dipole moment change 0. So, it is IR inactive. So, that is why it does not absorb IR energy. Now, process transmittance versus wave number. The result of spectroscopic process is a spectrum of various type of stretching and banding, that is stretches and bands of the covalent bonds in an organic molecule. Suppose this is an organic molecule. So, there will be a many stretching or banding in between the atoms like this and this, in between this and this, and also there is a stretching or banding in between these atoms. So, there are the lots of spectra due to this process. Now, what is stretching or banding and which type of, what is the process? During the vibration of molecule, if there occurs a change in dipole moment, it will lead to generation of oscillating electric field. So, when we applied the IR radiation, definitely it will produce electric field, and if the frequency of this oscillating electric field, it becomes equal to frequency of IR radiation or frequency of electromagnetic radiation, then definitely resonance will occur. Resonance will occur means energy can be transferred from the radiation of molecule or molecule to radiation, and this leads to IR spectra. So, basic is, suppose this is a molecule, and in molecule when we apply the electromagnetic radiation or fixed range, and which is 667 or we can say 400 to 4000 centimeter inverse, and when we pass this radiation, if there is a transition in between vibrational energy level, and when the transition will occur. So, if due to vibration, if there is a change in dipole moment, then definitely the oscillating electric field get created, and if the frequency of this becomes equal to frequency of this applied radiation, then the transition will occur. And since here we say that the bonds are like a spring, so we can apply Hooke's law, and as per Hooke's law, the wave number nu bar is equal to 1 upon 2 pi c under root k upon mu, where k is the force constant. If the force bond is strong, then the value of k get also high, and mu is the reduced mass, and reduced mass, it depends on the mass of the both atoms, and which is equal to yeah, we can say 1 upon mu is equal to 1 upon m1 plus 1 upon m2, or mu is equal to m1 m2 upon m1 plus m2. So, mu is reduced mass, k is force constant, c is the velocity. So, nu bar can be calculated. For a single CC bond, its k value is 5 into 10 to the power minus 5 with unit, and it double and triple bond, and it's basically doubles and triples for double and triple bond. So, we can say k is directly related to bond strongness basically. The force constant is a measure of the strength of bond. Thus, the value of stretching frequency of bond increases with increases of bond strength and decreasing with the reduced mass of the bonded atom. Nu bar is directly proportional to k and inversely proportional to mu. Since the triple bonds are stronger than double bond, then definitely IR frequency will also be high, frequency range. Let us consider reduced mass CH and CC. It's differ only 16 kilocalorie per mole. If we check the value, and due to reduced mass turn, these two bonds are similar strength, show up in a very different regions of IR spectrum. C single bond C, it shows the IR band at 1200 centimeter inverse, and CH it shows the IR band at 3000 centimeter inverse. Because its masses, if we calculate the reduced mass, mu is equal to m1 m2, that is 12 into 12 upon 12 plus 12, which is approximately this, and for CH it is approximately this. So, here we see that the reduced mass increases, the IR frequency decreases. Here the similar behavior is this. As the value of mu increase, the frequency, IR frequency get decreased. There are few questions we can find. The CH stretching vibration of chloroform is given. If the CD hydrogen is replaced, chloroform CHCl3, and if H is replaced by D, then find. So, we can find for CH and for CD. Here the mass is 1, but while for deuterium mass is 2. And next question, calculate the force constant of carbon monoxide. If this compound absorbs at this and reduced mass is this, we can find the value of K. Now, this is the important topic, normal modes of vibrations, that is types of vibrations. Normal modes of vibration is one in which all atoms in a molecule, they vibrate at the same frequency and in plane with each other. That is, there are types of vibrations or types of normal modes of vibrations when the molecules they vibrate. Now, first is stretching. So, in normal modes of vibration, we can say it is of two types. First is stretching and second is bending, because the bonds are like a spring and a spring can be stretched or bent. So, in stretching, the vibration or oscillation along the line of the bond. So, if stretching is like this, that either both are this side or both are towards the central atom, then this type of stretching is called symmetrical stretching. If the bond are stretched like this, one towards this side and then same time second bond is stretched outer the side, then this type of stretching is called asymmetric stretching. So, stretching it is of two types, symmetric or asymmetric. We can understand why this arrow. So, if arrow are on same side, then it is symmetrical, on different side that it is asymmetrical. Now, why bending? Bending means vibration or oscillation along the line of bond. Here the bending it may be in plane or out of plane. Now, in plane bending, again it is of two type, scissoring or rocking. Scissoring like a scissor, that is bend towards inward direction. Rocking, rocking like a rocking chair, either on this side or this side. So, in plane bending, it means it can be bent like a scissor or like a on a same side. Out plane, out plane it may be twisting or wagging. Twisting means if one is in front of wear, then definitely second is back to wear. So, twisting same side, and while wagging is this. So, we can say plus minus or plus plus. So, plus means in front of viewer and minus means back to viewer. So, I think it is clear. Symmetrical stretching, asymmetrical stretching, one bond is like this, bending, scissoring, rocking this side or this side, wagging either in front of viewer or both back to viewer, and twisting one in front, one back. Now, possible transitions. How many modes of transition in a molecule are possible? We know that total degree of freedom, if we count, it is 3n, where n is the number of atoms. So, total degree of freedom is 3n. Then the molecule, it may be linear or non-linear. If a molecule is linear, then type of translational. Translational means along x or y or z. So, the along translational, it will be motion will be 3. Now, rotation. But when we talk about the rotation in a linear molecule, it will be along only 2 axes, that is rotation will be 2. Then the remaining definitely it will be vibration. Total is 3n, in which 3 translational and 2 rotational. So, the vibrational transition it will be 3n minus 5 for linear molecule. But in case of non-linear molecule, same translational it will be 3, but rotational since it is a non-linear. So, the rotation may be of any axis along any axis. So, rotation again it will be 3. So, the remaining will be vibration. So, the mode of vibration for a non-linear molecule it will be 3n minus 6. So, for linear 3n minus 5. For example, examiner asks calculate the modes of vibration in CO2, and since CO2 is a linear molecule and there are 3 number of atoms. So, the total degree of freedom or total possible transition it will be 3, and that is 3 into 3, which is 9. But in 9, 3 will be translational, 2 will be rotational. So, the total vibrational mode it will be 4. So, in case of CO2, how many modes of vibrations? 4 modes of vibration, and these modes of vibration they may be stretching, symmetrical or asymmetrical, they may be scissoring, rocking or twisting, wagging. But in case of H2O, since H2O is the bent structure means non-linear, and in case of non-linear the mode of vibration will be 3n minus 6. Number of atom is 3. So, 9 minus 6 will be 3. So, in this the modes of vibration will be 3. So, in CO2 since the 3n minus 5 that is 4. So, here we can draw 4 CO2 and it is our choice. We can write symmetrical stretching, asymmetrical stretching, twisting or wagging. While in case of H2O 3n minus 6, 3n minus 6 means answer is 3. So, there are 3 possibilities. We can draw any symmetrical, they may be asymmetrical, there may be scissoring, rocking or etc. You can draw any 3. Now, how many modes of vibration do you expect from CO2, SO2 and CHCl3? So, I think CO2 is clear. SO2 again we can find from this. Suppose examiner asks how many modes of vibration in C6H6. In C6H6 it is a planar, that is non-linear. So, 3n minus 6. The number of atoms are 12, 6 atoms of carbon and 6 atoms of hydrogen. So, 12 into 3, 36 minus 6, the answer will be 30. So, in benzene we can say that the vibrations possible, these are 30. Same in CHCl3. CHCl3 structure is like this, and since Cl is more electronegative, so definitely there will be a change in dipole moment. So, it will be IR active. The number of atoms are 3, 4, 5, that is 15, 5 into 3, it is linear, non-linear. So, 6, that is 9. So, in chloroform the modes of vibrations, it will be 9. So, I think it is clear. Now, next is regions. We know that the range of IR is 667 to 4000, but in this most of the bands that indicate what functional group is present, it is called functional group region, and functional group region is 1400 to 4000 centimeter inverse, and in between these region we can find which type of functional group is present. And remember this point that IR spectrum is very useful to predict the structure as well as find out the functional groups. Their bands can be identified and used to determine the functional group present in unknown compound. The bands that are unique to each molecule similar to fingerprint are found in fingerprint region. That is 1400 to 4000 is functional group region, and below 1400 up to 600 is called fingerprint region. As we know that the fingerprint of two person can never be same, the same in a fingerprint, the IR peak or IR spectra of any two compound can never be same. It is very specific and which depends on stereospecific arrangement of the atoms. So, in 1400 to 4000, in between this up to 2000, the band observed due to double bond, that is due to presence of carbonyl CN or CC, the IR frequency is observed below 200 centimeter inverse and below 2000 centimeter inverse, and 2000 to 2700. In this range the absorption occur mainly due to triple bond, absorption by triple bond, and above this, that is 3400, 3600, it is basically due to bonds to hydrogen, or we can say single bond, which is OH, NH or CH, and that is why OH, due to OH IR frequency, it is observed at 3200 to 3600 centimeter inverse, which lies in this range and which is a functional group range. CN, it is approximately I think 2300, 23 or this. So, this carbonyl, it is about 1700 centimeter inverse, which lies in this range. So, I think it should be clear that for up to 2000 due to double bond, 2000 to 2700 or 2500 in some books there are, so triple bond, and up to 4000 it is due to OH bond, and due to single bond, C single bond, C, CN and CO, it is very specific and it comes in fingerprint region. So, what is fingerprint region? Although IR spectrum, it can be used as a fingerprint for the purposes of comparing the molecule, the 667 or 600 to 1400 range is called fingerprint region, and in this region IR spectra can never be same, and it depends on structure of the whole structure of the molecule, and it shows many band frequently overlapping each other, and this complexity limits its use to that of fingerprint, and it should be ignored by beginners when analyzing the spectrum. So, it is comparatively complex, but it is very important region. This is the IR spectra of ethanol. Okay. So, in ethanol, since OH group is there, so IR band, IR peak is band is observed about 32 to 36, and there are others due to CH stretching or CC stretching, bending or etc. So, these are the few average positions, and we will discuss all these positions or values and then how to calculate or how to find the structure in next lecture. Thank you.